Modeling in progress. Perfect. So today for the webinar, we welcome Antoine Monier. He's a postdoc at the Laboratory of the Future in Bordeaux in France. And he's going to talk about diffusiophoresis in sucrose gradients. And yeah, Antoine, you can thank you so much for being here. And because we tried many times to organize this webinar with Antoine, and now we are happy to have him. And you can start to share your slides and you can talk a bit about yourself, what you have done before, and then you can start to talk about your subject. Let's go. And okay, also anyone, if you want, you can ask a question to Antoine during the whole presentation so that there is more of a discussion than just a presentation. And so do not hesitate. Antoine, you can start.
Okay, is the sharing all right?
Yeah, perfect.
Yeah, okay. So, good afternoon, everyone. Thank you so much for the invitation, Leah and Michel, and for the organization of this wonderful series of webinar on rheology. So yeah, we'll just discuss a bit about myself for a slide. I feel a bit bad because I'm not really a rheologist myself. I'm more a soft matter experimental physicist. And during my whole research, I've been very interested in the interfacial flows and interfacial phenomena. So I did my PhD thesis in Institut d'Alembert in Sorbonne Université, a couple times ago. And here I worked a lot on the interaction between the solidification, that is to say the phase change from water to ice, and the coupling of the flow of water. And so this was really interesting topic, and as it gathered some heat transfer and solidification physics, and also some wetting and contact line dynamics. And so after that, I moved to Nice, where I met Leah and Michel. So maybe it's why I'm here today. And I pursued doing experiments, but this time on soap film physics and how fast soap film drains. And it gathered subjects and topics such as interfacial phenomena once again, and also friction in such tiny systems. And recently, so in September, I moved to Bordeaux, where I work at the LOF, and I study microfluidic topics that are related to osmotic phenomena and plant physics application. So I'm looking at how colloids move spontaneously under concentration gradients. And also, I'm very interested on how the membranes can be a good tool to select some solutes. But today, I'm going just to focus on this topic, which is will be the main part of my presentation. But of course, if you have any discussion you want to have at the end, please make sure to ask questions. So this is a topic I started in September in Bordeaux with quite a lot of people actually. Julien, who is a PhD in the lab, Benjamin, who really started an internship a couple times ago, and also it benefit from the internship and the collaboration with Brielle Burley and Daniel Ouyang, who are from the Department of Physics of Lehigh University in the USA. And I work as PI with Pierre Lidon and Jean-Baptiste Salmon, and we will be discussing the diffusiophoresis in sucrose gradients. Okay, so let's start the easy way. I think you all know what sucrose is because it's very an everyday life molecule in the human life. I mean, it's the sugar that we have the most in the agro-industry, up to almost 70% mass for the case of maple syrup. So if you go on a trip to Canada, make sure not to have too much maple syrup. And also, it is very used in the pharmaceutical industry for the excipients that you and the medicine that you eat. But in the lab, we are more concerned about plant physics. So really what we are doing is try to replicate and to mimic some osmotic phenomena that we find in plants. And so just a quick slide on how a tree works, because a tree is not like a human body. It doesn't have a pump. We have a heart, but the tree does not have a pump, and so it has to exploit the gradients of nature. And so there is two main vascular systems. The xylem, which transport the water from the roots to the leaf. At the leaf, you may know that there is the photosynthesis that transform water into sugar, and then the sugar is transported back to the regions that are growing with osmotic transport. And in fact, it's very useful to study this with microfluidic networks, because the dimensions of the two channels are like 100 of micrometers for the xylem, typically 10 micrometers for the phloem. And so in all those applications, there are, of course, strong sucrose gradients that emerge. Okay, just a quick slide about osmotic phenomena, because maybe some of you do not know it very well, and as I used to do when I arrived to Bordeaux. So, in fact, if you have two containers separated by a semi-permeable membrane, in fact, there is a flow from the container that contains water into the container that contains sugar, because it wants to dilute the sugar in the second container. Okay, and so this flow results in a sucrose gradient into the second container. And sometimes it is illustrated with this kind of scheme. So if you have a U-tube, okay, and with a membrane at the back, so you have a flow from the water that wants to dilute the sucrose of the second part, and this results in a height which is associated to the osmotic pressure. And in fact, the true definition of osmotic pressure is the pressure that you have to apply to the system in order to counterbalance this flow. Okay, so of course, the larger the concentration difference between the two tanks, the larger the flow, and so the larger the osmotic pressure. Okay, so now in the trees, we have big molecules that are transported also, such as nutriments or sediments or whatever. And so these are the dark spot you have here. And at this object scale, there is also two sucrose gradients that are present. If the object is big enough, it will sense the gradients from the back to the bottom. And also, it exists a gradient along the object itself, because it exists an interaction length between the sucrose molecule and the object. And this is represented here, where you have a zone where the molecule cannot go any further to the object. And this, in fact, gives an interaction potential between the solute and the surface, and it exerts a volumic force that is proportional to the solute concentration. And this leads to a building of osmotic pressure in these regions. In fact, it's a membraneless osmotic phenomenon. And so if you had the fact that you have a gradient on a certain direction, in fact, you have a spontaneous drift of the particle. Okay, so that is the drift of the particles. That is it's a diffusiophoresis drift, because it's arise from a concentration gradient. And then the drift is given by the interaction between the solute and the object. So you don't have to remember this formula. We'll discuss it a bit later, but it's given by this interaction between the object and the molecules, and also by the spatial osmotic pressure gradients. And of course, the sign of the interaction between the molecules and the object give you whether the object is going to go toward high osmotic pressure or towards low osmotic pressure. Okay, so it's a phenomenon that is well known in physics, and it has given recent interest with the development of microfluidic, because with microfluidic you can observe very easily the migration of objects such as colloids, for instance, that we are going to use today. And there was a lot of studies in the group of Lideric-Bocquet focusing mainly on salty solutes, such as the NaCl, you know, from the kitchen. Okay, and it's very convenient. Okay, so it's an experiment from the lab. If you just so there is a three junction. If you flow colloid and water, you see that you do not broaden the distribution. But if you flow now colloid and salt, you have the drift of the colloid of the curves. And if you do the inverse, if you flow colloid and salt at the center and water at the two exits, you will start to sharpen the distribution. So it's a very useful tool to displace objects quite passively. Okay. There have been also recent studies in the literature about neutral solutes. So here the geometry is a bit different than before. You have two compartments separated by a membrane here, and you can observe the colloid migration from one compartment to the other. And also back in, so last year, there is a work by Agdenis on the PEG 400, which is a polymer. And they show that there is a drift of the colloid that is going further down channels as you increase the solution, the concentration, sorry. So this is a well-known phenomenon, but there is few studies on neutral solutes, and also people are a lot focusing on macro quantities such as the extrusion length, for instance. And so the two questions I will try to ask today is: can we observe such a phenomena with sucrose, and can we measure the diffusiophoretic speed at which the colloids are going? So prior to explain you the setup, what is very convenient when you work with sucrose is, as it is very well known in the literature, you have a bunch of properties that are tabulated, even at high concentration, because today we are going to work up to 30% weight to be very close to what is happening in the plant's systems. So for instance, you have the specific volumes, that is the inverse of the density, that vary with the concentration. So is the viscosity, even if I will not discuss a lot about the viscosity today. And more importantly, the diffusion coefficient of sucrose also vary with the concentration. And all of these features will show arising non-linearities that we are going to take into account today. Okay, so what we want to do is to have a very controlled sucrose gradient using a microfluidic device. Okay, so for those of you who are not very familiar with microfluidic, just a quick slide on how we make our chips. So the first thing that we have to do is to make a solid resin design that we are able to form on the silicon wafer. And then after we pour some liquid PDMS, which is an elastomer, and we place this at the oven for about 2 hours. Then we unpeel the PDMS from the mold, and then we are able to stick it to a glass slide, and then to puncture it to inject water or liquid in the chip. Okay, so the geometry is the following. So we have a main channel here where we are going to inject our solutions. And this main channel is connected to smaller ones whose dimensions are typically 1 millimeter long and 50 millimeter wide. So if I do a close-up on one channel, the experiment will be the following. First, I inject water everywhere, and so I fill my secondary channels. Then I flush just an air bubble, and then I flush sucrose at T equals 0, and then I will impose a sucrose gradient that is going to develop in the secondary channels. Okay. This was the top view of the chip. Now we're just a side view. So okay, so the main channel here. So the sucrose is going towards the perpendicular to the screen. Okay, and you have the secondary channel here, which is 10 micrometer height, and so the large aspect ratio between the main channel and the secondary channels is here to ensure that there is no flow in the secondary channel. Okay, so this is a geometry that is very used when you study diffusiophoresis effect. For instance, it has been used by Shin and Bata a couple years ago. And to prevent any evaporation, that is to say the fact that we evaporate water through the PDMS, we plunge the chip underwater, so we saturate the environment with water. Then what we do is we flush first water with colloids. That is to say, we are going to place colloids on the secondary channels first, and we make sure, of course, that the colloids we are using match the density index of the sucrose water mixture. And then we are going to look at the experiment from the bottom with a microscope that is inverted. Okay. So one first video of the movie. So it will be accelerated around 100 times because the experiment lasts around 40 minutes. And I want you to focus on the difference of speed of the colloid that are at the entrance of the chips and the one that are at the close to the dead end channels. Okay, so I have also highlighted for you the channels, and here you have just a crop of an experiment because you have 1, 2, 3, 4, 5 channels. Okay, and at T equals 0, I will impose the sucrose, and first I have only water and colloid in the secondary channels. Okay. So when I play the video, you see the colloids that were at the very beginning of the chips that are invading quite fastly the channels, whereas the ones that were located further down the channels are not really moving a lot. Okay. What is very nice is I can do the experiment the other way around. Okay, no, so sorry. So if I look at some trajectories of my colloids, what this is just what I've explained, is there is a huge drift of the colloid that were close to the inlet, whereas the colloid that were almost at the end of the chips, they move much fewer. And the maximal drift velocity that we are going to measure is typically 3 microns per second. So what I was saying is that you can do the experiment the other way around. So first, I fill my secondary channels with sucrose and colloid, and then I flush pure water. And in fact, you will see quite the opposite. That is to say, if you focus on the colloid that are close to the entrance, they will go toward the water and finally escaping the chip. So this is the case for here and this one also. And then the colloid that were at the end of my channels, they are going to move towards the water, but quite slowly. And once again, if I look at the typical trajectories of Oh, okay. So I put a laser in my microscopes that are going to laser inside my channel, and then I will move my laser in all my channel, and so I can evaluate on every on 10 different position and over time what is the concentration of my sucrose over space and time. Okay. So here is once again a typical experiment of the Raman spectra. So it will give you some Raman shift, but don't bother with the units. What is very important is that this is the typical spectra for water. And when I'm going to play the video, you will see here that there is a peak that stands for sucrose that is going to grow as I will as the sucrose invade the chip. Okay, so if I play the video, this is what you see. You start to see a peak. So you have the color will stand for the time that you have here, and I'm looping over the different position. Okay, in space, and what you see that the further down the chip, the fewer the peak, and the closer to the entrance the the spectra, the higher the peak, but these gradients start to diminish in time. That is to say, the sucrose finally invaded all the chip. Okay, so it's quite nice because I have something that I have let's say a qualitative measurement of the sucrose invasion in my secondary channels, but I want to do something more quantitative, and so I need to calibrate the sucrose intensity ratio. That is to say, the ratio of the sucrose peak to the water peak. So to do so prior to the experiment, I prepare different solutions that I know the concentration, the sucrose concentration of, and then I measure the Raman spectra of all my solutions. So in color here you have the sucrose mass weight, and you see, of course, that if I look at sucrose 1%, is going to be just like almost the water spectra. And if I look at sucrose 30%, it's the yellow curve. You see a high peak of the sucrose. And then what I can do is I plot the ratio of the sucrose peak with respect to the water peak as a function of concentration. And then I can evaluate the sucrose concentration in my chip. From the previous experiment, I measure over space and time the sucrose-water ratio, and then I deduce the concentration. Okay, so this gives you this typical concentration field. So in y-axis is the time, in x-axis is the position along the channel. And you see that first I have only full water, which is the dark blue here. And then as time passes, the sucrose invade the chip quite fastly. And of course, it's faster at the entrance because I impose the sucrose almost immediately at the entrance, but at the exit, I have full, let's say, full sucrose only after a typical time that is roughly an hour. I can also look at the sucrose concentration at 5 different positions. So this is the plot you have here. So the sucrose concentration with respect to time and with different positions. So again, in green, it's very close to the entrance. So you see that the sucrose concentration saturates very fastly, but in blue, it's very close to the end of the channel, and it takes much longer time to reach the sucrose concentration that I had imposed at the very beginning. Okay, so we are quite happy with those measurements, but we wanted to model the sucrose concentration field. And so we propose a very, let's say, a simple equation to model this transport is that we have only diffusion of sucrose in the secondary channels. And then we write, so the sucrose concentration variation over time is given by the diffusion of the sucrose concentration. But we have to take into account that the coefficient diffusion of sucrose is varying with the sucrose concentration. We have two boundary conditions for this problem. At x equal L, so at the entrance, I impose my sucrose concentration, and at the end of my channel, I have a zero flux, a zero flux. And so I can solve this problem doing numerical solving. And this is the theoretical concentration field I get, which is rather similar to the one that we get experimentally. And to convince you once more, I can do the same trick as before, looking at just different position. And here I plotted in dark line the prediction of the model for the sucrose concentration over time. So we were quite happy that we recover quite nicely the sucrose diffusion into the channels. Okay, so now that I know my sucrose concentration field into my small channels, I can deduce what is the sucrose osmotic pressure. I recalled I did quite some time to evaluate the concentration, but the main goal is to predict the speed and the migration of my colloid. Okay, so I recall that is the migration of the colloid is given by the sucrose osmotic gradient times the interaction between the solute and the molecule. And now that I know my concentration, I can relate the concentration of the sucrose to the osmotic pressure. And once again, we have some non-linearity here because we deal with very concentrated sucrose solution. 30% mass is quite a lot. And so we deviate from Van 't Hoff law. Van 't Hoff law is just the law that we have for very dilute solute. So you have a linear behavior. And you see that in blue is the sucrose from the literature, the sucrose osmotic pressure from literature. So now that I know my concentration in my secondary channels and I know the relation between the pressure and the concentration, I can, in fact, deduce what is the osmotic pressure field in my secondary channel. So once again, here is the time. Now we non-dimensionalize the time. So little t is the dimensionless time, and little x is a dimensionless position. And here I divided the osmotic pressure by the Van 't Hoff law, and you see that we are always above Van 't Hoff law. But more interestingly, we can compute the osmotic pressure gradient because we know that the drift is supposed to be given with this quantity. And in fact, you see that the osmotic pressure gradient is very strong in the upper right regions, that is to say, close to the inlets at small times, and very weak far from the inlet, which looks like what we are having in the experiments. Okay, so just wrapping up before trying to match the theory with what we observe on the colloid displacement. So we have the sucrose concentration field in the secondary channels with the fact that the diffusion coefficient is a function of the concentration itself. We can then compute the pressure from the concentration. And finally, we can estimate the colloid drift with the pressure gradient, the osmotic pressure gradient. And so what we are going to do is just the next slide. that the only unknown in this problem is what is gamma. Gamma is once again, the physics of gamma is the interaction between the molecule and the colloid. But here I have no clue about what should this parameter be for the sucrose, okay? So what I do is I take all my trajectories. Here I just highlighted 3 of them, okay, for different starting position. And I shoot my numerical, yeah, Leah?
Yes, we have questions here. Sorry.
No, no problem.
Just to understand a bit more like your model before, you
Yeah,
choose coefficient, yes, the second equation.
yeah,
How did you choose the model, and did you think about maybe the impact of the aspect ratio of the channel or other parameters? And how did you choose alpha exactly? Because
yeah,
eventually there are different regimes when you change alpha. I don't
yeah.
know. It's a
No,
question.
it's a very good question. Maybe I just went a bit fast on
A bit
this, but
fast on
in
that one.
fact, I
Yeah.
don't choose anything.
Yeah, yeah.
It's given by the literature's value on the sucrose. So here you have, let's say, 3 different publications that shows the diffusion coefficient of sucrose
It's
divided by
always linear. Yeah.
yeah, in fact, it's quite convenient to work until 30% mass because after it's not linear anymore.
What
So,
happens just after? It's like,
in fact, it's more or less saturates.
yeah, okay. It's a trait. It was
So
my,
we fit the experimental data. It
yeah,
gives us an alpha that we use in the model
in
just
the
here.
model. Okay. Okay, okay. Thank you. Sorry.
No, that's all right.
You can continue.
So yes, so what I was saying is that we shoot for different gamma the numerical solving of this equation to get the trajectory of the colloids. And then you see at the beginning I fail my trajectory, but at one point I can find a gamma that passes through the experimental colloid drift. And then I can find for each trajectory the best parameter that fits my my trajectory. So the only experiment I showed you now was the when I impose 30% mass sucrose and colloid that were 500 nanometers, and then I can have a distribution of what is gamma for every colloid I can track. But I can do different experiments. For instance, here, this is the case for the reverse experiment I showed you. So where you have first sucrose and then you flush water. This experiment is, sorry. Oh, yeah. This experiment changed the colloid side up to 1 micron diameter. And this one, I changed the initial concentration of sucrose. And you see that you have some dispersion among the experiment, but there is no strong effect on gamma with the experimental parameter. And then you have like a dispersion of the experiment that gives gamma, that is to say 1.3 10 to the minus 16 whatever. But I will try to discuss the physics of it for the next slide. But in fact, we did it for 265 colloids over the experiments. So okay, so it's quite nice to have such value of gamma, but what can we relate it to the physics? So now we are back to this quite let's say mathematical expression for the interaction between the solute and the molecules. In fact, it tells you that it's given by the potential of interaction between the molecule and the particles. In fact, why also the people were doing such stuff with salt is for salt solution, it's given by the Debye length. Okay, but here we deal with neutral solutes, so we don't really know what we should put here. So we put the more basic potential, that is to say the hard sphere potential. So when I'm outside of this region, the potential of interaction is 0. And when I'm inside this region, the potential of interaction is infinity. Okay? And this, I can compute what's gamma here. And what it gives me is that I can have, let's say, it gives me the size of this interaction layer. And so I can go back to the experimental data, and now I can translate it into the size of what is this interaction zone. And in fact, what I find is something that is very close to 5 angstrom. And we typically find the size of the sucrose molecule if you average it to be like a sphere. And so we were quite happy, that is to say, it's a way to evaluate what is the interaction between the colloids and the sucrose molecule. Okay, so just some partial conclusion for you now. So we showed that there is a diffusiophoretic that can arise from sucrose gradients, and we were able to predict and match experimentally the trajectory that we observe with the theoretical predictions of the literature. And we deduce from this work an exclusion distance that is quite close to the sucrose, the molecule equivalent radius. And so some perspective that we are typically working on right now is we are trying to understand why there is a dispersion in the experiment. For instance, here I show you different colloids, but that have the same, roughly the same starting position. So it should gives the same trajectory, and you see that there is some noise in the data, and we think like it might come from two origins. First is a Brownian motion that can induce deviation from the prediction, and then is the fact that we have also diffusiosmosis that's superimposed to diffusiophoresis. And so just to conclude in two slides. In fact, it's quite easy to add the fact that we have Brownian motion as a one dimension. So you just have to add to the colloid trajectory the Brownian motion term, and it gives you an envelope that in fact explain a bit why the trajectories are a bit scattered. But you can also do 1D Brownian motion simulation. That is to say, I can solve my differential equation with a Brownian term, and I can in fact simulate different colloidal trajectories at a different position, and then I can say what is the best gamma of those let's say numerical experiments. And if I do it for every starting position, I can get also another distribution of gamma, which is the one that you have here in pink, and I can superimpose it to the distribution that we have in the experiment. And in fact, it explains quite a lot the scattering of the data that we see in the experiment. And lastly, we also know that everything I just told you about diffusiophoresis is also happening at the walls of the channels. Meaning that also at the walls of the channels, you have a surface, and then the sucrose cannot go and penetrate the surface. And though this arises in what we call diffusiosmosis, which is really the same phenomenon as diffusiophoresis, but diffusiophoresis relates to the particles, and then diffusiosmosis relate to the walls. And so in diffusiosmosis, there was no fluid flow, okay? So it's just really colloid migration, but diffusiosmosis can lead to some, in fact, strong flow over the channels. What we believe and what we think, and we have arguments for that, is that this phenomenon, in fact, is very limited in our case because the diffusiosmosis phenomenon is a zero net flux phenomenon, and in fact, if you average it enough over the size of the channel, you don't see diffusiosmosis. And in fact, if I compute the typical time for the colloid to go up and down the channels, I get typically 100 seconds, which in an experiment that lasts an hour, you have the fact that the colloid is doing roughly 30 back and forth. And so in average, this flow cancel out to zero. And so we are quite confident that we only see diffusiophoresis. Lastly, of course, if you couple these two phenomena, you have like a perfect Poiseuille flow, okay? And this can also lead to some dispersions of the colloids and some Taylor-Harris expansion of the initial distribution. And also there is a very nice paper by Alessio and collaborator, and we are trying to add this phenomenon to explain the scattering of our experimental data. So with that, I thank you for your attention.
Thank you, Antoine. Thank you so much.
Thank
So
you
do
very
we have?
Sorry.
Yeah, no, go ahead. Yeah, sorry.
You can go. I have other questions. You go.
No. I was just asking if somebody from the audience had questions.
Ah, okay.
So
if there is,
otherwise,
if there is anyone from the audience that has any questions. Hi, everyone, by the way. Hi, Emilia. Hi, Jose. Hi. Okay, if you have any questions, do not hesitate.
I have a question. So I understand how osmosis works, and in that case, only the water molecules are allowed to pass through the membrane. But in this gradient case, where you have a solute gradient, for example,
Yeah.
and because of that, there is a kind of osmosis pressure. My understanding is, in that case, will not the solute also try to mix and create a reverse pressure against the osmosis pressure?
Yeah, in fact, you're right. There is something related to buoyancy that can induce solute recirculation and then like mix the concentration. This is what you are referring to, right?
Yeah.
In fact, there was a theoretical studies about that, and in fact, the fact that we choose such a small height h is to minimize as much as possible this phenomenon. In fact, I think I have some additional slide for you. Yeah. Okay, so the BOC effect is given, in fact, by the Rayleigh number, which is the how a natural convection plays in this problem. Okay, and it's given by this quantity, and you see that it's related to h to the power 3, and in fact, if you have secondary channels which are 10 micrometer height, which is very small, the Rayleigh number is very, very small, and so we expect buoyancy effect to be very limited, and so there is almost no recirculation effect in the secondary channels.
Okay, but still it's not, like, I understand your math, but still it's not clear. Like, even if there is no gravity, let's say there is no gravitational effect at all, still I'll assume that in terms of chemical potential, it will be preferred that all the solutes mix uniformly along the two. If the solvent is same, for example, let's say water solvent, if the same solvent is there, it will try to uniformly mix all over the volume, right? Like, isn't that what the intuition says about the chemical potential?
Yes, in a sense, yes, but I mean, we are quite concerned about all that, but then this is why we did, in fact, the ramen experiment, right? So, but the fact that only diffusion explains the solute concentration over time in the channels indicate that there is at least very limited other physical mechanism at play.
So it means basically that it's primarily a local effect, not a global effect.
What do you mean by that?
So I can understand that locally there can be some fluctuations in solute densities because of some other reasons. Maybe something has to do with the ions, presence of ions or something like that. So I can understand that the fact that I'm saying that it will try to uniformly spread all over through diffusion, that may not happen because of those local barriers. But I don't know, like maybe you understand that better.
I don't know, but the fact is there is only this ingredient to explain the solute concentration field. So I mean, in fact, we choose also H to minimize all kind of these effects. So
Okay, thank you.
thank you.
Thank you. Is there any question from the audience again? Julien, Luca, Jose, Milia. Okay, actually, my question was about the aspect ratio and the impact on the flow, but we already had a bit this discussion. And I don't know, Michelle, if you have any questions directly. Oh, Michelle is. Oh, I am dead. I am dead. Okay. Ça fait 2 fois.